Good afternoon, everybody. Stuart laid a good platform there on what our control options are, but in the forest genetics group at Scion, we're in the long game. We're interested in breeding for resistance for a more long-term strategy for how we can deal with these diseases in our forestry estate. Why do we need to breed for disease resistance? Well, I think to most of you in this room, it's probably fairly obvious. Foliar diseases cause growth loss. Dothostroma needle blight is estimated to cost close to $20 million per annum. This includes not only the growth losses, but also the operational cost of applying sprays. Cyclonusma needle cast is estimated to cost nearly twice as much. And then red needle cast, the new kid on the block. We don't know exactly how much of an impact this is having to date. Some estimates, there was a study by Peter Beets from Scion which showed that we were getting close to 40% annual growth losses in a single year of defoliation. Now, Stuart and I can't remember if Mike presented that as well. It's rare to see repeated defoliation events of that severity, but at that scale, it's got to be having an impact. And if we're wanting to explore chemical control options, well, obviously that's going to have a cost as well. So what we'd really like to be doing, ultimately, is to be able to deploy lines that are resistant in the areas that we know are prone to diseases. We want to minimise our dependence on these chemical interventions as much as possible, although always we'll have those tools in our back pocket when we need them. Now, we have our three main diseases. We also don't want to be putting all our eggs into one disease basket. We want to be able to have trees which are ideally resistant to lots of these different pathogens. And some work that we've shown to date shows that yes, we've got resistance to these diseases is heritable, and in some instances there is cross-resistance. Some work that's been done by our team at Scion, am I pushing the right button? Has shown, I'll move away from that, has shown good correlations between the resistance that we're seeing for Dothostroma needle blight and for Cyclonusma cast, as high as 0.78 here in the trials that we looked at, which is really great because it means we can select for one of those diseases and make simultaneous gains for both. Red needle cast, while it's not correlated with those other diseases, it is not negatively correlated either. So we still have the option just to include that as a separate trait in our selection strategies. So that's great. We're in a good position to implement disease resistance in our breeding program. There is a genetic basis and it's heritable for all three of our main candidates. Red needle cast, as has been mentioned by the previous speakers, is a relatively new disease, and we're still in the process of collecting information about this disease and how we can get the right information to have selection in our breeding programs. And to this end, we've done a lot of work screening material that is hopefully of relevance to the industry going forward. We started with the laboratory workhorse, which was the detached needle assay, which you've heard a little bit about already this morning, and we spent several months screening material from the radiodopine breeding companies' 13, 14 elite clones, which have been deployed in regional trials at least 12 different sites across New Zealand over the last few years. We sampled across the 63 families that are represented in that population, and we screened on average about 6 individuals from each of those families to give us a total of 400. Heritability using the detached needle assay was found to be about 0.39, and that's, again, a really great result using an artificial lab system. We can see from this graph here in the middle of my slide, this shows the average response in terms of the size of the lesion that each of those individuals developed. Most of them all sit in a big clump in the middle, but there are definitely some individuals which are falling out at the very top, which are our more susceptible individuals, developing longer and more lesions, and some individuals down at the other end of the spectrum which developed no or very few lesions of small size. These would be our candidates for more resistant individuals. These observations, as we know, and we as scientists love to put caveats on everything, and you'll need to forgive us for that, but it's been all in an artificial lab system, and before we go and make recommendations out to industry that you guys take off and run with, we want to make sure that we've given you the right advice, because those trees are going to be in the ground for a long time. And to date, the evidence is stacking up that backs the story that we're seeing. Having a look at the histopathology, so having a look at the pathogen growing back out of those needles, comparing a resistant and a susceptible individual based on this graph that I've shown, we are seeing support that these two classes of individuals behave differently in the way the pathogen behaves on needles from those plants. no, wrong one. Oh, no. This work has recently been published as well, which is, as a science organisation, is really great and shows that there is recognition for the work internationally that we're doing, that this work hasn't been done, as previous speakers mentioned, very little has been studied on Phytophthora pluvialis, the cause of red needle cast. It's not generally a problem in other parts of the world, but the other parts of the world will be watching. This data has also been provided in the form of rankings to the Radiata Pine Breeding Company, and as soon as pollen becomes available for these individuals, hopefully we'll start to see some selections being made so that we can start having resistant lines being deployed. So as I mentioned earlier, this work has been done in detached needle assays, which has allowed us to identify our resistant and susceptible individuals, but it's an artificial system, and we want to start moving this to more of a real-world situation. So we started to have a look at some on-plant assays. Some of you in this room may have heard Nari speak previously about some of the fog chamber work that we've done, where we've got an artificial chamber where we can mist up the room and expose plants to sprays of spores and then see how they behave while they're continuing to grow. We've also put some trees out in the forest in pots and seen how they behave when they're exposed to natural inoculum falling from above. And this has shown us that while the detached needle assay has been great, it's the dynamics of the infection process and tracking that infection process over time that is actually probably more informative in the long run. Having a single infection and how you respond to that is important, but it's also how that corresponds to the next round of infection and the next round of infection and that gradual build-up of inoculum within a tree and within a forest. And I think that Ralph will speak a little bit more around the modelling work that has been done in that space later on. What we've done recently, and is an ongoing piece of work, is to establish a mini field trial. So this is as real-world a system as we can hope to get, where we've taken individuals across that spectrum of resistance that were identified in the laboratory, and we've put those out, multiple clonal copies, in a stand out in Kinleith Forest, where we know there have been reports of red needle cast in previous years, and the hope is for us as researchers, not the forestry companies, that we will see more disease out there and we'll see some natural infections, and we'll be able to go back and confirm that what we've seen in the laboratory systems is stacking up with all these pieces of evidence going forward. So, as I said, this trial will allow us to monitor and validate what we're seeing. It's 48 different clones that are there, and at this stage we're going out monthly and we're doing health assessments on these individuals. At the same time, we're collecting some needles, which we're putting into our freezers, as our scientists have also been developing molecular techniques where we can go in and we can detect the DNA of the actual pathogen, and we can say whether it's there or not. We can also say how much of the pathogen is there, as hopefully an indicator of the degree of infection that we're seeing. All of this is giving us improved phenotyping techniques, because to date, having that key phenotype, knowing what is the best way to assess this disease, is still something that's probably a little bit murky. Throwing all these new in-field diagnostics techniques at the disease, as well as using some more of the modern remote sensing techniques, which Grant Pierce will speak to later, is allowing us to start to get a better sense of how this disease is progressing in this trial over time, before we necessarily see the classical symptoms of what we recognise as a red needle cast outbreak. We will have this data which we can then retrospectively go back to and actually have a look, or were there some signals that we could have picked up on earlier if we'd known to look for them. We're also wanting to, because we're geneticists, we want to have a look within the pedigrees as well. We've looked at a particular set of families. We want to start looking, can we go back as well? Let's go back and look at the parents and even the grandparents, and can we track this heritability of this disease through the pedigrees? We've also been recently granted access to the RPBC's full-scale trials as well, so we'll be going into those as well and having a look, are we seeing disease in there, and just building up this portfolio of evidence to support the data that we've seen to date. As part of the genomics program, which we'll hear a bit more about tomorrow, we're also wanting to start having some genomic estimated breeding values. So for instance, once we've trained our models on how to predict RNC susceptibility, we can then go to trials that don't have disease outbreaks. We can collect the genotypes on those individuals and we can make predictions. Is this trial likely to be susceptible or resistant? Do we need to intervene with chemical controls, or is it likely to be okay? And obviously that information can feed back into the breeding program as well. So in summary, Yes, we have shown that there is a genetic basis for disease resistance for most of the foliar diseases that we are concerned about in New Zealand, and breeding has the capacity to reduce growth losses, which will minimise our dependence on chemical sprays and ultimately increase profits for the industry. We've shown that there is good cross-resistance between the diseases Dothostroma needle blight and Cycloneusma needlecast. This means that we can screen for one of these diseases only, and the likely candidate here would be Dothostroma, because we can screen for this disease at an earlier age. It's easier to screen for because the canopy is lower down, and we can save money by only having to do one set of assessments, and we can make simultaneous gains for both diseases. We then add red needlecast as a separate trait because it's not negatively correlated, and we can make gains against all of our major foliar pathogens. We've also provided provisional red needlecast rankings based on the work that we have done to date in the elite clonal population, and these have been provided to the Radiata Breeding Company, and once pollen becomes available, these rankings will be used in doing some crosses to produce hopefully some red needlecast resistance material. We're also doing in-field validation using the improved phenotyping techniques that I've already mentioned, namely the qPCR, which is the molecular diagnostic, as well as using some remote sensing techniques. And ultimately, we want to start comparing with parents of these populations and get some full trial estimated breeding values and also the genomic estimated breeding values, and to start to more and more tie all these different pieces of information together and get the best predictive tools that we can. So I'd just like to acknowledge the Radiata Breeding Company, not only for some funding support for some of this work, but also for access to their germplasm, as well as Hancock's Forest Management for access to sites within their forest and to land to plant our mini field trial on. We've received a lot of support from the LRAY Centre in terms of modelling work, and then there's a whole lot of folks from Scion and the Healthy Trees, Healthy Future program, and lots of hands in the back who've been doing all these assessments. It is a large operation to do this work. So on that note, I'll hand over